Okay, now let's go back and talk about direct methods, that is Gaussian elimination based methods. These are really a lot more robust than iterative methods. Iterative methods may be faster for nice sparse positive definite matrices, but with my partial differential equation solver I have iterative and direct methods, but I mostly rely on the direct methods because for complicated non-symmetric systems, which occur all the time, typically iterative methods may not converge at all or may not work very well. So direct methods are still to be preferred for general systems. And well, we already saw that if you have an n by n system and you solve it using Gauss elimination, it takes order n cubed work. But what if you have a sparse system like the ones we've been talking about for iterative methods? Well, we already saw that you can reorder the unknowns and have a band matrix, and then it takes a lot less time to solve the band system. It's still Gauss elimination. You're just taking advantage of the fact that outside the band the elements are all zero. So we've already talked about band solvers then. For a sparse system, if you can reorder the unknowns and the equations, that is the rows and the columns, and get all the non-zeros inside of a narrow band, like if it's tridiagonal, or usually it's possible to get it to a relatively small band, then you can take advantage of the sparseness by using the fact that below the band nothing fills in, above the band nothing fills in if you don't do pivoting. If you have to do pivoting, then some fills in, but still for a large system with a small band, outside the band it's all zeros and mostly stays zeros except for some diagonals that add in here. So you can take advantage of sparseness by putting into the band form and cut down on the work tremendously. But surprisingly, you can sometimes often do much better than that even. That's what we're going to talk about now. So remember, we're still talking about Gaussian elimination. It's just a question of ordering the unknowns to minimize the amount of fill-in and therefore the amount of work, take advantage of zeros as much as possible. And to see that it might be possible to do better than a band solver, here's a typical band matrix. The x's are non-zero originally, and the pluses fill in. And look a little more closely here. So this is typical band solver. Everything outside the band is zero and stays zero because we're not going to do pivoting in this case. If we did, we'd just add some bands up here, but let's assume no pivoting, which was not necessary for this positive decimal system. Then outside the band, it's all zeros and stays zero, so band solver can cut down on the work tremendously. But notice that the band solver basically assumes that everything inside the band fills in, and typically that's not the case. There'll be some fill in, but the band solver has to assume that everything fills in, so it does a whole lot more work than necessary. So even the band solver does a lot more work than necessary because it has to deal with all these elements that could be avoided if you were more careful. So that brings us to sparse solvers, which are, remember, we're still talking about Gauss elimination. Band solvers, DLI and EQ, and these are all just based on Gauss elimination. It's just a question of ordering the rows and columns, i.e. the equations and unknowns, in such a way that there's least fill-in and taking advantage of the fact that there's not much fill-in, taking advantage of the sparseness of the matrix. If it's not sparse, then none of the band solver and sparse direct solvers won't do you any good. But if assuming that sparse matrix, iterative methods take advantage of that because when you multiply by A, it's only order nz work. But direct solvers, that may be fill-in. You want to minimize the fill-in. Well, here's a real simple example that shows the general principle behind these sparse solvers. Here are two 8 by 8 systems, and they're actually exactly the same, except that for the second system we move the first row to the last and the first column to the last. So we reordered them, the unknowns and the equations. So this is basically exactly the same system. Now if you use Gauss elimination, you see the entire matrix is going to fill in on this one, because you take a multiple this to knock that out, and those all fill in. Multiple this, knock that out, those all fill in. So by the time you've finished with the first column, the entire matrix is filled in. So this is going to actually take you still order n cubed work. It doesn't take advantage of the sparseness at all. On the other extreme, this one takes full advantage of it, because so you take a multiple of this and add it to that to knock that out, then you have to take a multiple of this and add it to that, but that doesn't add any non-zeros at all. Take a multiple of this, you only got one element to knock out, so you take a multiple of the second row and add it to the 8th row. You have to take a multiple of this and add it to that. Again, there's no fill-in at all, and you can go all the way to upper triangular form without any fill-in at all. And this is an n by n system that looks like this. It's going to be order n work for the whole thing, whereas this is going to be order n cubed. So that shows that reordering the unknowns to minimize fill-in can be very important. In particular, notice the idea is to delay the fill-in as long as possible. The rows and column that have all the non-zeros in it, you put them last. Here you put them first. They're going to mess everything up if you put them first. They won't do any harm if you put them last. That's the general principle, is to postpone fill-in, because that causes further fill-in later on. And so there are a number of sparse direct solvers. This is again just Gauss elimination. The key is ordering the unknowns and the equations to minimize fill-in. And also they have to be careful not to, well, they don't want to store the entire matrix, obviously. Even the band solver doesn't do that. But they'll store only the non-zeros and the elements that fill in, and that obviously complicates things. They have to figure out where it's going to fill in and only store those locations. They have to store only the non-zeros. So they're very complicated codes. We're not going to make any attempt to write any, but just to show you that they can be very efficient. Here's a linear system of 113 unknowns. This was actually generated by finite element method PD2D in a real legitimate problem. And we already talked about this. See, the x's are non-zero to begin with. The pluses, there's fill-in. The band solver really doesn't take advantage of any of these zeros. The band solver takes advantage of the zeros outside the band. It skips all those, but it doesn't take advantage of the fact that it's still mostly zeros inside. The sparse direct solver would. Somehow, it's complicated, but and so this is a band ordering, and if you use a sparse direct solver with this ordering, then it will cut the amount of work because it won't touch the elements that it knows are going to stay zero. But it can do better than a band solver. And here's what happens when you take exactly the same matrix and reorder them. A Harwell routine MA27, which is used by PD2D with permission. This is a sparse direct solver that reorders them using basically a minimal degree algorithm, which the basic idea is that at each stage of the elimination, the next unknown should be the one that generates the least possible fill-in. So again, the principle is to try to delay fill-in toward the end, and you can see that happening here. So again, here, this is the same matrix, just a different reordering. And again, the x's are non-zero in the original matrix. The pluses are zero originally, and they become non-zero. And you can see there's some fill-in, but not much compared to the band solver. It doesn't have a small band. That's the interesting thing here. It really doesn't, it has almost a max. The band is essentially n. It's the maximum possible band. So if you used this ordering with a band solver, that would be terrible. But if you use this ordering with a sparse direct solver that only keeps up with the non-zeros and not the elements that are going to fill in, obviously that's complicated, but it does it. Then there's actually a lot less fill-in. and therefore less total work. And for this particular problem, as I said, this is 113 by 113, so it's actually still pretty small matrix. There are 1,041 non-zeros in the original matrix, and then with the band ordering, 1,508 more elements fill in, but the band solver has to keep up not only with those, but the ones inside the band that don't happen to fill in. So the band solver has to store 8,000 elements basically, whereas the sparse direct solver, there are only 450 non-zero elements that fill in, compared to was 1,500 with the band solver. Even if you use a sparse direct solver with the band ordering, this cuts the amount of fill in, and the amount of work is cut proportionally. So in this example, the work is cut. Well, band solver has to store 23 elements, and not only store them, but it's going to have to deal with them, take multiples of them and add them to others, even though they're zero. Whereas the sparse direct solver only has to deal with these 450 extra zero elements that fill in, as well as the ones that were non-zero originally. So sparse direct solvers are way beyond the scope of this course. The details, they're complicated, but this will give you an idea of what they do. Basically, they just have to, it's still Gaussian elimination, just plain old Gaussian elimination, but they reorder the elements not so that there's a minimum band, but so that there's minimum fill-in, and how they do that is complicated, but we've given some idea. Now, I actually did give you one homework problem. It was a 1D finite difference problem, and I believe part A, the finite difference method generates a tridiagonal matrix, and you solve that using tridiagonal solver, and that's only order n work. Basically, tridiagonal solver is a band solver with bandwidth of 1. But now part B, the boundary conditions are periodic, and now the finite difference system it's tridiagonal, but there's an extra element in the top right and the bottom left. So it's basically tridiagonal plus 2 more non-zeros, and they're in the extreme corners. So basically, band solver is no good now because the bandwidth is maximum possible. But you can see that it's still possible to solve this in order n work, because it's similar to that example we gave at the beginning of you take a multiple this and add it to that, then this fills in, multiple this and add it to that to knock that out, and this, well, this is already non-zero. Then basically the last row and the last column fill in and nothing else. So it's actually possible to write a little routine that you can see that it's order n work still, because only the last column and the last row fill in. This one's not too complicated. Of course, you don't store the matrix as an n by n system. That would be extremely inefficient. You store the 3 diagonals A, B, and C, and then you have to also internally save D, which is the last row, and E is the last column, because they're going to fill in. And if you want, you can see the details of how this is done. It's a little more complicated than just a simple tridiagonal solver, certainly, because you have to keep up with that last row and the last column, but it's fairly straightforward. And here's the code. In matrix algebra, you learned that a square system of n equations and n unknowns, if the matrix is singular, there's either no solution or many solutions. If the matrix is non-singular, then there's always a unique solution no matter what B is. So basically, there are good matrices and bad matrices. Square matrices, we're going to always solve square systems, same number of equations as unknowns always in here. So if the matrix is is either singular or non-singular. Singular ones are bad matrices. They always have no solution or many. Neither one is good. Or they're good matrices, non-singular, and there's a unique solution. But in the real world, when you use computers, there's a gray area between good and bad matrices. A matrix can be ill-conditioned. That means nearly singular. And that's what we want to talk about in this section. What do we do if a matrix is nearly singular? What happens? Well, best way to look at it is starting out with a 2x2 system. When you're solving a 2x2 linear system, what are you doing? You're intersecting two lines. And if the two lines are parallel, there's no solution or many solutions if they're the same line. If they're not parallel, then they intersect in a unique point, and there's a unique solution, and everything's fine in matrix algebra anyway. But in numerical analysis, what if the two lines are nearly parallel? Well, then theoretically there's a unique solution, but it may be very hard to find, and you can see that by thinking that the first thing you do before you even try to solve a linear system is you copy the coefficients of the matrix on the right-hand side into a finite precision word on the computer, and thereby changing it a little bit by changing the elements of A and B by machine precision. And if the two lines are nearly parallel, you see that's going to change the intersection point, changing the intercept of one of the lines or the slope of one of the lines. Most anything is going to change the solution a whole lot if they're nearly parallel, the kind of scissors effect. So before you even try to solve the linear system, you've changed the exact solution a whole lot. So you can see that if two lines are nearly parallel, you're almost bound to get bad answers no matter what method you use. So that's 2x2 system, and 3x3 you're intersecting three planes and so forth. But the idea is basically the same. If the system is nearly singular, if it's ill-conditioned, means nearly singular. Well-conditioned means not nearly singular. If it's ill-conditioned, then there's basically nothing you can do about it. You're doomed before you even call the Gaussian elimination or iterative solver. And so all we're going to do in this chapter is figure out how to issue a warning. How can you measure ill conditioning? Find out a way that you can at least tell the user to be careful because your system is nearly singular. Well, an obvious measure of how nearly singular a matrix is, since we know that if the determinant of a square matrix is 0, it's singular. If it's not 0, it's non-singular. You might say, well, the determinant is a good measure of how nearly singular. If a determinant's nearly 0, it's nearly singular. Well, that's true in a way, but you have to be careful because, see, if you multiply a matrix through by a constant, that changes the determinant. For example, this matrix here and this one represent exactly the same two lines, and if you take the determinant of this, it'll be extremely small, and the determinant of this is nearly 1, but it's only because B is basically D multiplied through by 10 to the minus 10, so that's determinant's not a good measure of ill conditioning because it depends on the scale. The most common way of measuring ill condition, though, is called the condition number, which is defined as the norm of A times the norm of A inverse. And the reason that's useful comes from this theorem here, which basically says if you solve a linear system AX equals B, and you change B by vector delta B, small amount, change the matrix by matrix delta A, a small amount, then the relative error, because see this, assuming delta A is small, this is nearly 1, so it basically says the relative error in the solution is less than or equal to this thing, which is the condition of A, times the relative error in B plus the relative error in A. So that basically says that this thing here, which we call the condition number, is an amplification factor, and you see that the change in B is going to be around machine precision just before you even try to solve the system. The change in A the relative error in relative error in A, the matrix elements, is going to be machine precision also at best, because you just can't store numbers more accurately than that. And so this basically says the relative error in the solution is less than or equal to the condition number of A times the machine precision. That's kind of our rule of thumb here. So this is an amplification factor. Ideally, if this is 1, we'll see that this is always greater than or equal to 1. If it's 1, then the relative error in X is on the same order as the relative error in B and A. In other words, a small change in B or a small change in A will make a small change in X if the condition number is small. If the condition number is huge, 10 to the 10th, say, then a small change in B or a small change in A will make a large change in the solution. That's the scissors effect. Well, you might say, well, we haven't even talked about solving the system. We're just talking about the changes in the solution due to small changes in the right-hand side in the matrix due to simply, putting them into the computer word. They'll be order machine precision no matter what you do. And so this is an amplification factor. And we haven't said anything about solving the system, but it has been shown that if you solve this system using Gaussian elimination with partial pivoting, it's important to do partial pivoting. If you don't do any pivoting, then you can have terrible error even if the matrix is well conditioned. So we're going to assume that you do partial pivoting, so you do pivoting. Then it has been shown that the result from partial pivoting with Gaussian elimination with partial pivoting is the same effect as changing A by machine precision, relative error in A. So basically what we're saying, it's just kind of hard to explain more rigorously, but basically the effect of Gaussian elimination with partial pivoting is on the same order of magnitude as the effect of just changing the elements of A and B by relative amount of machine precision. And so that's even if you solve the system supposedly exactly with Gaussian elimination and partial pivoting, you're still going to have this kind of an error. A condition number of A times the machine precision. That's kind of our rule of thumb, that the relative error in X due to everything, the change in B, the change in A, and the errors made by partial pivoting and Gaussian elimination, the effect of everything is on the order of the condition number of A times the machine precision. Well, the theorem just says that its relative error is less than that. It could be a whole lot less, but it's statistically not likely to be a whole lot less. So we'll take it as a rule of thumb that the relative error in the solution is approximately condition number of A times the machine precision on that order of magnitude, maybe off by a factor of 100. Well, notice that the condition number of any matrix is always greater than or equal to 1. Why? Because it's the norm of A times the norm of A inverse, which is greater than or equal to the norm of A times A inverse. That's any matrix norm. The norm of our product is less than or equal to the product of the norms. And that means the norm of I and the norm of I is 1. So the condition number of A is always greater than or equal to 1. It's 1 ideally. If your matrix is the identity, then you're going to multiply your machine precision by 1, and your relative error in the solution will be on the order of machine precision. Any other matrix, the condition number is bigger than 1, and the bigger the worse it is. If its condition number is 10 to the 10th and machine precision is 10 to the minus 15 or so, then you can expect a relative error in X of on the order of 10 to the 10th times 10 to the minus 15th, which is 10 to the minus 5. So basically you lose 10 significant digits. The most you can expect for, well, we're talking about double precision on MATLAB, of course. MATLAB is always double precision, so machine precision on MATLAB is going to be like 10 to the minus 15th, and that's the ideal error. That's the best you can hope for, a relative error in the solution of 10 to the minus 15th, and the condition number amplifies that. So if you have a condition number 10 to the 10th, then instead of 15 significant digits, you'll have about 5. You lose 10, approximately. This is only an estimate. Also notice that if you multiply the matrix by a scalar, the scalars cancel out. You'll get the norm of, if you multiply A by alpha, you'll get absolute value of alpha times norm of A times absolute value of 1 over alpha times norm of A minus inverse, and the alphas and 1 over alphas cancel. So if you multiply a matrix by a scalar, that doesn't change the condition number. Well, it shouldn't, because it doesn't change how much error you're going to get. Multiply both sides by a scalar doesn't make a bit of difference as far as round-off error is concerned. Unlike the determinant, with the determinant you multiply through by a constant, and that changes the determinant greatly, so it's not a good measure of conditioning, but this is. Well, let's do a MATLAB example, and we're going to use the Hilbert matrix, which is a famous ill-conditioned matrix for large N. The components of the Hilbert matrix are defined as 1 over I plus j minus 1. Not at all obvious why that's ill-conditioned, but it's known to be ill-conditioned, and the bigger the Hilbert matrix is, the more ill-conditioned it is, so we're going to use it as an example. And by the way, it doesn't mean that large matrices are going to be more ill-conditioned than small matrices necessarily. You can have a large identity matrix has a condition number of 1, which is the best possible, and you can have a 2 by 2 matrix that has extremely high condition number, which is bad. So size isn't the problem. It's just that this Hilbert matrix happens to be such that the bigger it is, the more ill-conditioned it is, and that's a known fact. We'll see that's the case. Okay, here's a little MATLAB program that we're going to test. Remember that with Gauss elimination, and we're going to call GEL, that's my little Gaussian elimination routine that simply solves hx equals b, n by n h, using Gaussian elimination with partial pivoting. But if you call most any linear system solver, the results will be essentially the same. So we first set up the n by n Hilbert matrix. Well, we'll pass in an n. We're going to try different size Hilbert matrices. So here's the definition of the n by n matrix, Hilbert matrix. Then I rig it so that the exact solution is 1, 1, 1, 1, 1, n1. So I set the true solution equal to 1, 1, 1. And then I simply multiply h times the true solution to get my b. And then I call GEL to solve hx equals b. And since b is h times xt, it should come back with x equal to xt. In other words, all the components of x should be exactly 1 if there's no round-off error. And so we calculate the error. That's the error vector. That's the difference between the Gauss elimination with partial pivoting solution and the true solution. Again, that's entirely due to round-off error. There's no truncation error here. Gauss elimination is supposedly exact, so it's all round-off error. Then I'm going to calculate the residual. Now, what's the residual? That's hx minus b. Again, that should be exactly 0 if there's no round-off error, because x should be the solution of hx equals b. So both the error and the residual should be exactly 0 vectors if there's no round-off error. So I calculate the norm of the error and the norm of the residual. And then for comparison, in our rule of thumb says that the error should be about the condition number times the machine precision. EPS is going to be like 10 to the minus 15th for MATLAB. So we'll compare the estimated error using our rule of thumb with the actual error norm and calculate the condition as the norm of h times the norm of h inverse. That's our definition. So that's the condition number. So we're going to compare our rule of thumb estimate of the error, which is condition number amplification factor times the machine precision, with the actual norm of the error. And then we're also going to look at this residual, which you'd expect to be larger the more ill-conditioned the matrix is also. Okay, so let's call our program Hilbert. We'll solve a 3 by 3 Hilbert matrix. And the error, the norm of the error is around 10 to the minus 15th, which is what you expect. Condition number is 748. Well, that sounds bad, but it's really not too bad. only, order 10 squared, 10 cubed. So our rule of thumb estimate is the condition number times the machine precision. So our rule of thumb says the error should be about 10 to the minus 13th. It's actually 10 to the minus 15th. Well, so we're off by two factors of 10. The residual is real small also. Okay, so let's try with a larger Hilbert matrix, 6 by 6. Now the error norm goes up to 10 to the minus 10th, and our rule of thumb estimates 10 to the minus 9th. It's only off by a factor of 10. That's not bad for a round-off error. That's round-off error is art. Truncation error is a science. And then, but strangely, the residual is still around machine precision. So let's try a larger system. Again, the bigger the system, the more ill-conditioned. That's just a feature of Hilbert matrices. Now the error is like 10 to the minus 4. And our estimated error is like 10 to the minus 3. Condition number is 10 to the 13th, which means the condition number estimates we lose about 13 digits of accuracy, decimal digits. We have 15. Ideally, if the matrix is identity or a very well-conditioned matrix, you'd expect a round-off error in a relative error in the solution of 10 to the minus 15th. But the condition number is 10 to the 13th, so you lose 13 of those 15 digits. And, well, according to this, you've got about 4 of them left, but that's close enough. But now this funny thing, the residual is still extremely small. Well, let's try one more. Let's try 15 by 15 Hilbert matrix. And now the condition number is 10 to the 17th. That means you lose 17 digits. Our estimate, we lose 17 digits. You only had 15 to begin with. That means your solution is pure garbage. And in fact, it is pure garbage because the norm of the error is 6. Remember, the solution is 1, 1, 1, 1, 1, all 15 ones. And a norm of the error of 7, that means you're getting things like 8 and minus 5 and, getting total garbage. And yet, here's the strange thing, though. Notice the residual is still around 10 to the minus 16th. So think about that a minute. How is that possible? The error, the exact solution is 1, 1, 1, 1, blah, 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 1. And we're getting things like 7 and minus 6. And, there's an error of like 7, much more than 100% error. Total garbage in your solution. And yet you go back and plug that into the equations, hx minus b, and you get almost exact satisfying it. How can that be? Well, to understand how the residual can be so small, even though the error is so large, let's go back to our 2 by 2 example where things are easiest to understand. Okay, we've got an extremely ill-conditioned matrix. That means the two lines are nearly parallel, and that means anything is going to change the solution a lot. Just when you store your elements of A in the right-hand side in the computer, you change the solution a large amount because of the scissors effect. Move one of the lines a little bit, the intersection point moves a lot. And then it doesn't matter what you do after that. Basically, we said it's been proven that Gauss elimination with partial pivoting, which is what we're doing, has essentially the same order of magnitude effect as just changing the elements of A and B. So same effect. So how could we get a solution so far from the true solution and yet small residual? Well, notice that both of these points here almost lie on both lines. See, if you change one line, you have a large change in the solution, but there are a lot of points that almost satisfy both the equations. In fact, that's basically what makes it so hard to find the exact solution, is because there's so many good solutions. There's so many points in here that are close to both lines that it's hard to find the one that's exactly on both of them numerically. So that's not that surprising then that the residual could be small. Basically, Gauss elimination with partial pivoting is returning something that it's not. It looks like garbage when you compare it to the quote true solution, but it's not really garbage. It's in here close to both lines, or all the lines if there's 15 equations. So that's how come. So Gauss elimination with partial pivoting, if you remember, my program doesn't give up unless it absolutely has to, unless they get an exactly zero pivot. It keeps going and hopes for the best, and you see that's not such a bad idea after all, because you get something that if you want it to be real close to the exact solution, you're going to be disappointed. But if you just want it to nearly satisfy all the equations, you might be happy after all. Well, the iterative methods discussed in the last section, Jacobi, Gauss-Seidel, and successive over-relaxation, are surely the easiest methods to program and understand, but there are other iterative methods that are more widely used, and a lot of the best ones are based on the conjugate gradient method, which is outlined here. We won't go into detail on where this comes from, but there it is. We're solving AX equals B. Now this is strictly for a symmetric matrix A. So conjugate gradient method is strictly for symmetric matrix A. There are variations of it for non-symmetric matrices, but it's basically for symmetric matrices. And it can be proven, and we do, that it's guaranteed to converge if A is not only symmetric but positive definite, just like the Gauss-Seidel and SOR methods are guaranteed to converge for symmetric positive definite systems, but they actually converge for a lot more, and so does the conjugate gradient method, but it's guaranteed to converge if matrix is symmetric. In fact, it has a very interesting property that it's guaranteed to converge exactly within n iterations. So it sounds like that has the best features of direct and iterative methods. It's guaranteed to converge to within round-off error in a finite number of steps, but in fact it's really an iterative method, not a direct method, because the property that it's guaranteed to converge in n iterations is almost useless in practice because of the round-off error accumulates, and if it hasn't converged by n-1 iterations, don't expect a miracle the next iteration. And in fact, usually it will converge long before that. If it doesn't, it's not doing a very good job. So it's basically an iterative method. Okay, well, it's easy to figure out how much work is done each iteration. What's hard is to know how many iterations are done, just like the other iterative methods. And well, if you look at an iteration here, there are several operations that are dot product of two vectors of length n. Those are dot products. Add a multiple of one vector to another. Those are all order n work, so 4 or 5 times n here. But then the most work is calculating this APN. So you have to multiply a vector by the matrix A. That's where most of the work comes in. If A were full matrix, that would be order n square work, but of course if you had full matrix you shouldn't be using these iterative methods, you should use Gauss elimination. So we're going to assume that A is normally sparse. In that case, A times the vector is a lot less than n square iterations. In fact, it's going to be basically nz multiplications, where nz is the number of non-zeros, because you just have to multiply each element of each non-zero of A times an element of P. So the overall work is going to be order nz, which typically nz will be number of zeros will be a small multiple of n, at least for the like the 3D example we tested other methods on last section. No matter how large the matrix is, there's only at most 7 non-zeros in each row, so nz is like 7 times n. So the overall work is order n if the number of non-zeros is a multiple of n. Even if it's a good bit bigger, it still should be a lot less than multiplying by a full matrix. But then it was shown that the speed of convergence, the number of iterations it requires to converge, depends very much on the condition number of A. If a well-conditioned matrix A, that is the largest, well, we're talking about symmetric matrices, so the eigenvalues are non-zero and mostly positive definite matrices, so they're real, and so the eigenvalues are not only real, they're positive. So let's assume A is positive definite. Then the speed of convergence depends on the condition number, that's the largest eigenvalue divided by the smallest eigenvalue. So if you have an eigenvalue real close to zero, that means A is nearly singular and it's going to have a large condition number, it's going to converge slowly. So that means that it could be advantageous to multiply A by another matrix, B inverse, which makes the condition lower, and that will make it converge faster. You might say, well, why not just multiply by A inverse? Then you get the identity, which has a condition number of 1. It'll converge really fast. Well, yes, but each iteration, you're going to have to solve Bx equals something. You don't actually find the inverse, but you'll have to solve a system with matrix B, which means that that had better be quick, because you have to do that every iteration, so there's no advantage of taking B to be the entire matrix. But you could take B to be the diagonal part of A, for example, and then it's easy to solve Bx equals something if B is the diagonal part. Or there are other choices, but we're going to only look at the diagonal. So one obvious choice would be to take B to be the diagonal of A, and when you multiply A by B inverse, that will decrease the condition number. And then here's the modified conjugate gradient method, where you're basically solving B inverse A x equals B inverse B, except so you're going to have to multiply matrix A times P as before, but you're also going to have to multiply by B inverse, which you don't really multiply by B inverse. That means you solve Bx equals AP. So if B is the diagonal part of A, or any diagonal matrix, then that will be very fast order n work to solve that system, and then order nz work to form that. So the conjugate gradient method applied to B inverse A x equals B inverse little b is this, and again it's still order n and plus order nz, where nz is the number of non-zeros of A. Well, here's a Fortran version of the conjugate gradient method, DCG, that's the diagonal conjugate gradient. That means we're going to use the conjugate gradient method, but first multiply by D inverse, where D is a diagonal matrix, usually should be the diagonal part of A, but it could be the identity, in which case it's just the ordinary conjugate gradient method, or it can be some other diagonal matrix. But anyway, it's a preconditioned conjugate gradient method, preconditioned by a diagonal matrix. You see, if you multiply A by D inverse by its diagonal part inverse, you'll end up with a matrix all of whose diagonal entries are 1. That should normally make the condition number smaller. You're kind of rescaling things. If you have one row that's real large or real small, you're going to be multiplying it by the inverse of the diagonal and make it more palatable. Anyway, so the user passes in the matrix, and notice A is not an n by n matrix. That would be extremely inefficient. We're assuming A is mostly zeros, and so you only pass in the non-zero elements of A, the nz non-zero elements, and those are going to be in the rows I row and column J column. In other words, A of I contains the non-zero element in I row of I, comma J col of I. So those three provide all the non-zeros of A. And you see, the only place that this matrix is actually used is to multiply by a vector P. So here's where the most work takes place each iteration. It's where you're just multiplying this vector P by A, but you only multiply by the non-zero elements, so it's only order nz work, and everything else is order n work. These are some dot products and adding some multiples of a vector to another. So It's easy to figure out how much work each iteration. The question is how many iterations have to be done. That's not nearly as obvious. Same as for SOR and Jacobi and Gauss-Seidel. It's easy to figure out that the number of operations per iteration for those methods is also proportional to NZ because we saw that the work is each iteration is proportional to the number of non-zeros in A, just like it is for conjugate gradient. But how many iterations does it take? Well, we went back and tested DCG. By the way, diagonal, we tested it on that same three-dimensional finite difference method that we tested the other methods on here. And by the way, that's the big matrix that's, it's M minus 1. It's an M by M by M grid, so there's M minus 1 cubed non-zeros and M minus 1 cubed unknowns in. And remember, each row of the matrix contains at most 7 non-zeros. There's a 6 down the diagonal and minus 1s scattered around, so and it is symmetric. So the diagonal is all 6s, which means it really doesn't do any good to multiply by D inverse. That's the same as multiplying by the identity, because just to multiply the identity. So this is basically just the normal conjugate gradient method. And we applied it to these three cases, that is 10 by 10 by 10 grid, which means 729 by 729 matrix, and then 20 by 20 and so forth. And with M equal to 10, it took 25 iterations. That's less than the best SOR optimal omega, and took 56 in this case and 115 in this case. So it took less than half as many iterations as optimal SOR. Remember the star, that's the best choice of omega, which you have to normally determine adaptively or something. It seems to be converging faster, at least fewer iterations than even SOR. And the advantage is that you don't have to guess at an omega or choose it adaptively or figure it out theoretically. So there's no troublesome parameter to choose for the conjugate gradient method. So it seems to be a better choice for this problem.